Hello my friends and welcome back to the You Can Do TV channel. In this video we will explore the modern technologies and incredibly heavy machinery used in bridge construction in China and Japan. The Bower pile drilling machine is a powerful and versatile piece of equipment used in various construction projects, including high-rise buildings. This machine is known for its durability, modern features, and strong working capacity. The machine is equipped with a standard cat engine, a modern drilling system, and high-quality drill bits. It has an operating weight of up to 70 tons, a traction force of 260 kilonewtons, and a bore depth of 57 meters, making it suitable for a wide range of working conditions. Some of its key applications include drilling piles using casing wall pipes. The pile drilling machine can drill piles while using casing wall pipes, which can be stabilized with drilling solution. It can also be equipped with hydraulic shakers for extracting forces. Drill piles with chicken gut drill bits, CFA system. This system allows for drilling piles with or without additional extensions, depending on the specific requirements of the project. Fixed pile drilling. The machine can perform fixed pile drilling, providing a stable foundation for construction. The machine's specifications include a bullhead engine, KDK 245K, with a rotation torque of 245 kN and a maximum rotation speed of 30 RPM. The bullhead pressing system can exert a pressure pulling force of 260/260ths of a kilonewton, and its itinerary varies depending on the drilling system being used. The machine also comes with a main winch with hydraulic cable tension operation, a mast tilt system, and various standard drilling equipment. The machine is equipped with advanced control and monitoring features, including display panels for tracking hydraulic functions, error messages, depth measurement for the main winch, and more. At the construction yard, prefabricated reinforcing bars are meticulously assembled and prepared for installation. These bars are crucial for providing the necessary strength and support to the bridge piers. To lift and position these bars, a robust rough terrain crane with an 80-ton lifting capacity is employed. During the hoisting process, several factors are considered. Engineers must account for the potential deformation and yielding of the reinforcing bars, as well as any misalignment issues. To address these concerns, equilateral angle steel measuring 65 by 65 is used as reinforcement. It is securely affixed to the vertical main reinforcing bars using fixing brackets. Furthermore, a suspension fulcrum is attached to the reinforcing bars to facilitate lifting and placement. To ensure that the load on the suspension support is evenly distributed, height adjustments are made using a chain block through the suspension support, typically made of H-steel material. This meticulous process ensures that the suspension is lifted and placed at the predetermined position, contributing to the overall stability and strength of the bridge piers. China's high-speed railway network is renowned for its remarkable infrastructure, with a significant portion of the trains running on impressive flyovers and bridges. To construct these bridges, China has developed an advanced and highly efficient system, exemplified by the extensive use of box girders. The box girders, the major components of these high-speed railway bridges, are engineered from a combination of structural steel and pre-stressed concrete. What makes this construction process truly remarkable is the level of pre-engineering and prefabrication involved before the girders even reach the construction site. The production of these box girders undergoes a meticulous process consisting of 9 stages and 18 procedures. This elaborate procedure takes a total of 42 days to transform raw materials into the sturdy and reliable box girders. Each of these girders boasts an impressive weight of 1,000 tons and is designed to endure the harshest conditions, including challenges such as wind erosion, water intrusion, high temperatures, and extreme cold. Once the box girders are fabricated, they are assembled on site, meticulously bolted together, forming a solid and dependable base for the high-speed railway bridges. China's rapid economic development and urbanization have led to an increasing demand for efficient transportation networks, including high-speed railways and modern bridges. To meet this demand, the construction industry in China has turned to heavy machinery and advanced construction techniques. The use of heavy machinery plays a pivotal role in the construction of high-speed railway bridges, which are essential components of China's transportation infrastructure. In this article, we will explore the role of heavy machinery in constructing bridges and the construction of high-speed railway bridges in China. Heavy machinery is crucial in the construction of bridges and high-speed railway bridges in China for several reasons. First, it significantly accelerates the construction process, allowing for the completion of projects within tight schedules. Second, heavy machinery ensures precision and safety in bridge construction, reducing human error and accidents. Third, these machines can handle heavy loads and perform tasks that would be nearly impossible for manual labor alone. In China, the deployment of heavy machinery has enabled the rapid expansion of high-speed rail networks and the construction of impressive bridges. One example of heavy machinery used in bridge construction in China is the 550T girder transporter, such as the KSC 900 manufactured by Kuro Artelt GmbH Leipzig. These specialized machines are designed to transport precast concrete bridge components from the precast yard to the installation site. Precast concrete components are used extensively in bridge construction in China, as they offer high quality, consistency, and durability. The 550T girder transporter can efficiently move these large and heavy components to their intended location with precision, reducing the risk of damage during transport and installation. In the construction of high-speed railway bridges, precision is paramount to ensure the safety and efficiency of train operations. Precast concrete girders, bridge segments, and other components must be precisely positioned and assembled to create a seamless and robust structure. Heavy machinery like the KSC 900 plays a pivotal role in this process, allowing for the careful transportation and placement of these elements. High-speed railway bridge construction is a critical part of China's transportation infrastructure. Some of the most prominent high-speed railway lines in China, such as the Wuhan-Guangzhou, Zhengzhou-Xi'an, and Beijing-Shanghai routes, rely on robust bridge structures to support the high-speed trains. The KSC 900 and other similar heavy machinery ensure that the construction of these bridges meets the required standards for safety and performance. A specific application of heavy machinery in high-speed railway bridge construction is the full-span launching 820-ton box girder system. This system is used for projects like the Taiwan High-Speed Rail Project C250 in Taichung, Taiwan. Launching trusses are large structures used to place one section of a span of the overhead portion of a bridge. In the case of the full-span launching 820-ton box girder system, it is capable of handling extremely heavy girders, allowing for the construction of high-speed railway bridges with large spans. The use of such heavy machinery enables faster construction of bridges and minimizes disruption to existing rail networks, ultimately reducing the time it takes to complete high-speed rail projects. Efficiency is a key driver for the adoption of heavy machinery in high-speed railway bridge construction. The deployment of these machines streamlines construction processes, allowing for rapid assembly and minimizing downtime. Additionally, heavy machinery can work under adverse weather conditions, further ensuring that construction schedules are met. In China, where the demand for high-speed rail services is immense, these advantages are crucial to keeping projects on track and delivering transportation solutions to the public. Furthermore, the safety of both workers and the eventual users of the high-speed rail network is paramount. Heavy machinery minimizes the risks associated with manual labor, reducing the potential for accidents and injuries. The use of machinery like the 550T girder transporter and the full-span launching 820-ton box girder system not only ensures the precision of construction but also enhances overall project safety. China has made substantial investments in its transportation infrastructure in recent years, and high-speed rail has been a focal point of these efforts. High-speed rail networks offer a convenient and efficient mode of transportation, connecting cities across vast distances and driving economic growth. To accommodate these high-speed trains, robust bridges must be constructed to support them, and heavy machinery has been instrumental in achieving this goal. The rotational construction method across bridges, transforming bridge engineering in the realm of bridge construction. Innovation has always been the driving force behind remarkable advancements. The rotational construction method across bridges is a prime example of how engineering ingenuity can reshape the landscape of infrastructure development. This revolutionary approach has left an indelible mark, notably in projects like the National Highway No. 1 Wugu to Yangmei Section Widening Project, Plan C904A. Let's explore this innovative method, its unique application in the challenging context of the Wugu to Yangmei project. The rotational construction method across bridges represents a paradigm shift in bridge engineering, offering a fresh perspective on how we build critical infrastructure. It departs from conventional construction techniques, introducing an innovative way to assemble bridges efficiently, with precision, and minimal disruption to the surrounding environment. At its core, This method relies on several key principles: axial end and movable end. The bridge structure is divided into two main components: the axial end, serving as the stationary pivot point, and the movable end, which can be repositioned using mechanical equipment. Mechanical mastery. The method leverages a sophisticated array of mechanical equipment, including hydraulic jacks, support frames, guide rails, and counterweights, to orchestrate the precise relocation of the movable end. Precision in process. Construction follows a meticulously planned sequence: track beam support frame erection, track beam installation and advancement, main beam hoisting for the rotating section, beam rotation and closure, and removal of temporary facilities. The rotational construction method found its ultimate test in the National Highway No. 1 Wugu to Yangmei section widening project, Plan C904A, undertaken in New Taipei City and Taoyuan City, Taiwan. This colossal endeavor featured a total bridge length of 4,179 meters, with the steel bridge weighing a staggering 11,273 tons. The project faced significant challenges due to its unique location and demands. To navigate the highly sensitive area of debris avalanche, from 37K plus 400 to 39K plus 100 on the upper north side of the Zhongshan Plateau, the northern upper line of the Wuyang section had to be repositioned to the side of the south lower line. This complex adjustment presented the need for two long-span bridges, each with a 390-meter curvature radius, to avoid interfering with the existing Zhongshan-Gao traffic. The result was two spanning bridge units, each designed as three-span continuous curved steel bed plate steel box girder bridges. The bridge length measured an impressive 486 meters, featuring main spans of 216 meters, marking these as the largest span steel box girder bridges in China. The Linku Crossing Bridge, a vital component of this project, stretched from 39K plus 781 to 40K plus 267 and faced its unique set of challenges. To traverse the Linku climbing section and cross four on-ramps and off-ramps at the Linku area interchange, four existing roads, and the Taoyuan International Airport connecting MRT line, the bridge had to contend with a longitudinal slope of 4.96% and a height of about 30 meters. These intricate demands led to a bridge deck width of up to 20.2 meters, a variable cross-section ranging from 4 to 9.2 meters, and a massive steel box girder weighing around 8,700 tons. Amid these complexities, the project required an innovative construction method capable of meeting its distinctive requirements. Liangang, the project's contractor, collaborated with China Steel Structure Company to pioneer the rotational construction method for the first time in China. This unique approach was chosen for its ability to address the project's intricate challenges efficiently and precisely. The rotational construction method divided the Linku Crossing Bridge into two rotating sections on the south and north sides, using piers P4A01 and P4A02 as the axes of rotation. Temporary facilities were erected between these piers to facilitate the movement of the movable end, equipped with track beams measuring 3 meters in height and 2.5 meters in width. Guide rails were installed on these track beams to ensure precise southward and northward rotation. To support the weight and movement of the track beams, the installation adopted a pushing method. Each track beam was divided into sections, with propulsion equipment including vertical jacks with a lift capacity of 200 tons, horizontal jacks with a lift capacity of 50 tons, and propulsion hydraulic equipment. In practice, the process of advancing the track beams was an intricate dance of synchronization. Taking RGA as an example, the first 3 sections were assembled on the north side support frame, and horizontal and vertical jacks were deployed. This pushed the beam southward with a 1,000 mm hydraulic stroke, with the vertical jack raising to support the beam's weight. This sequence was repeated, advancing the beam by 10.5 meters. Tunnels are vital infrastructures in our daily lives, facilitating the smooth passage of cars and trains. The construction of tunnels, especially in mountainous terrain, requires advanced technology and substantial effort. Here is an overview of the general steps involved in tunnel construction. Setting up the portal. First, the construction site for the tunnel is prepared, defining the area where excavation work will take place. This area, known as the portal, serves as the central focus of the construction process. Explosive charges. Once the opening is created, it is filled with explosives. These explosives are used to break apart the rock formations and support the progress of the tunnel. After loading the explosives, a blast door is securely sealed, and the detonation process is carried out. Muck handling. Following the explosion, the handling of excavated material, which may include rocks and soil, is necessary. This process involves using wheel loaders to load the material onto dump trucks, which transport it outside the construction area. Structural reinforcement. To ensure the stability of the tunnel, special concrete is sprayed onto the tunnel walls immediately after excavation. This helps prevent collapses and strengthens the structure. Additionally, support structures, such as rock bolts, are installed by drilling holes, inserting bolts, and grouting to secure the tunnel's integrity. Final lining. Once the structural work is complete, the tunnel's interior is further reinforced. This involves covering the tunnel walls with concrete, forming the final lining of the tunnel. Waterproofing. To prevent water leakage, waterproof sheets are installed in the tunnel. Specialized formwork is used to create the correct shape for the tunnel lining, and concrete is poured into the gap between the existing structure and the formwork. After allowing the concrete to cure for a couple of days, the familiar tunnel shape is established. To create these underwater foundations, a precast cofferdam system was employed for the first time in Minnesota. This innovative approach began with the placement of a prefabricated steel framing system that served as a work platform. The platform featured circular openings that guided the placement of the steel casings, which are integral components of the caissons. These caissons extended through a series of challenging layers, including water, muck, sand, gravel, and soft sandstone, before reaching the bedrock beneath the river bottom. To ensure the foundation's stability, crews drilled an additional 25 feet into the bedrock, using massive drill bits measuring up to 7.5 feet in diameter. This process removed a substantial amount of material, requiring 2,500 dump truck loads to be transported to a landfill. Once the casings were clear of all materials, reinforcement bar cages were installed, and concrete was pumped to create solid foundations. A transition component, known as a footing, was then built above the caissons to support the pier columns. To create a dry working area for this critical construction phase, a cofferdam was installed around the prefabricated deck, which had been used as a work surface until then. Afterward, a concrete seal was poured underwater and allowed to harden. Once the seal had set, The water inside the cofferdam was pumped out, providing a dry environment for the construction of reinforced concrete footings. The world is currently ushering in a new era of cruises. Large cruise ships exceeding 100,000 to 200,000 tons are becoming a reality, and the popularity of spacious and beautiful ocean views, like the Inami Blue, is booming worldwide. However, in Tokyo Port, just before the Harumi Pier, the Rainbow Bridge has a clearance of only 52 meters, which makes it impossible for large cruise ships with a height exceeding 60 meters to pass through, and it is not adequately meeting the demand. To address this situation, the Tokyo Port Authority is advancing the development of the Tokyo International Cruise Terminal, a new terminal facility using artificial land in the sea area next to the Rainbow Bridge. The Tokyo Godo Tetra Construction Joint Venture has been awarded the contract for the construction of the new passenger ship pier at number 13, the core of this project, from fiscal year 2017 to fiscal year 2019. The construction was carried out using the latest pier construction technique, the jacket method. The construction of the Tokyo International Cruise Terminal will transform the outer sea of the Rainbow Bridge into the Aomi 3 area in Odaiba. The Tokyo Fudo Tetra Tenho joint venture is responsible for installing the core components of the terminal pier, including the jacket section. The foundation of the jacket pier consists of steel pipe piles with a diameter of approximately 1.5 meters, reaching a depth of about 50 meters into the seabed. Once completed, the apron for cruise ships to dock will be approximately 430 meters in length, 30 meters in depth, and 11.5 meters deep, totaling more than 2 hectares. In February 2019, the site area was already equipped with a 550-ton crane for pile driving operations using steel pipe piles to be used as the main support structure for the terminal. Next to the pile driving, large gantry cranes with steel pipe piles were laid out. The diameter of the steel pipe piles is approximately 1.5 meters, and they extend over 10 meters in length. They are carefully lifted to avoid damaging the 30-ton steel pipe piles. The process of pile driving is a crucial element that determines the success of the jacket installation, so precise guidance from land-based total stations, using a piling guidance system with a margin of plus or minus 7 centimeters accuracy, is employed to guide the steel pipe piles to the exact location. With the hydraulic hammer positioned over the island, the pile driving begins. Initially, the steel pipe piles are driven into the seabed by applying a low-impact energy. The position and vertical alignment of the steel pipe piles are carefully checked during this phase. Subsequently, the hydraulic hammer is operated continuously, adjusting the impact energy according to the condition of the seabed to ensure the piles are securely installed. During the final stage of pile driving, data, including rebound, both striking energy, and other parameters are recorded and analyzed to confirm the support capacity of the seabed. Once the pile driving for the steel pipe piles is completed in the early morning, the main event begins with the installation of the jacket. A 1,600-ton revolving crane vessel, which has traveled nearly 1,000 kilometers from Hyogo Prefecture, arrives at the site area. The experienced workers on board get ready for the crucial and nerve-wracking operation. The seasoned workers' faces reflect the tension and focus required for the task. As dawn breaks, the massive jacket becomes visible at the tip of the central breakwater, shrouded in morning mist. After a long voyage of almost 1,000 kilometers from Hyogo Prefecture, the jacket arrives at the site area. To ensure its stability and prevent deformation or damage, the vessel's motion during transportation is analyzed in advance, and restraints are used to secure the structure. The crane vessel, equipped with a lifting capacity of 625 tons, is ready to hoist the 1,300-ton jacket onto the steel pipe piles. With the pile driving completed, the last restraints are released, and the final step of hoisting the jacket into position begins. Using 4 hooks connected to steel wires, the jacket is carefully lifted, ensuring a balanced load on each of the 15 steel pipe piles. This operation, which involves inserting 15 steel pipe piles simultaneously, requires a high level of technical expertise honed through experience. Up close, the sheer size of the jacket is truly overwhelming. A team of experts closely monitors the movement of the jacket during the hoisting process. They use the crane's level indicator to track the overall movement and report on the status of the steel pipe piles and the jacket. With meticulous attention to detail at every station, the highly precise jacket installation is achieved through teamwork and collaboration. With the successful completion of the jacket installation, the site enters the final stage, including the installation of precast floor panels. The precast panels are manufactured in a yard located outside the central breakwater embankment, transported by a 400-ton slewing crane ship, and installed directly at the offshore construction site. A total of 124 precast floor panels, of various sizes, are being installed. Reinforcement bars are coated with epoxy resin for corrosion protection against saltwater. The installation of asphalt paving covers an area of approximately 7,000 square meters. The asphalt paving was carefully compacted and finished to meet the specified width, thickness, and density. Temperature control during the process was closely monitored to ensure the material's quality. Afterward, the roller was used to thoroughly compact and finish the paved areas. The asphalt pavement covered an area of approximately 7,000 square meters. In June 2019, with the completion of the jacket installation, the final phase of the site involves finishing work, including the installation of precast floor panels. With the jacket installation completed, the final phase of the site involves finishing work, including the installation of precast floor panels. The Tokyo Gate Bridge, a triumph of modern engineering, is not just a connection between Tokyo and its port, but a testament to human ingenuity and the ability to overcome formidable challenges. The construction of the bridge's lower truss girder is a remarkable achievement, and the Kawada Group played a pivotal role in bringing this colossal structure to life. The lower truss girder, a critical component of the Tokyo Gate Bridge, was no ordinary piece of construction. With staggering dimensions, it measures 232 meters in length, 35 meters in height, and 24 meters in width. The steel weight alone amounts to approximately 6,000 tons. When considering the lifting equipment required for installation, the total weight is a jaw-dropping 7,000 tons, which equates to about 1.5 times the mass of the iconic Tokyo Tower. It was assembled on the ground in Ariake, Koto Ward, Tokyo, and Futsu City, Chiba Prefecture. However, the sheer size and weight of the girder presented a formidable transportation and installation challenge. To overcome this, the lower truss girder was transported by sea and lifted into place by 3 large crane ships. The project required 2 3,700-ton floating cranes and 1 4,100-ton floating crane, each with the capacity to handle the immense weight of the girder. These ships played a critical role in the intricate process of hoisting and placing the lower truss girder with precision and safety. The construction and installation process were documented through a fixed-point camera, offering a mesmerizing view of this engineering marvel. The role of heavy cranes in bridge construction, particularly in the assembly of bridge girders, is of paramount importance in Japan. Let's explore the critical role of heavy cranes in bridge girder construction in Japan. Heavy cranes are essential for lifting and placing bridge girders, the horizontal load-bearing structures that form the backbone of a bridge. In Japan, bridge girder construction involves the use of massive precast concrete or steel sections. These girders can weigh anywhere from 100 to 900 metric tons or even more, depending on the bridge's design and span. Heavy cranes are used to hoist these colossal components into position with the utmost precision. Japan's construction industry boasts a wide range of heavy cranes with impressive lifting capacities. For bridge girder construction, crawler cranes are commonly employed. These cranes come in various sizes, with lifting capacities that can range from 100 to 1,500 metric tons. Specific numbers vary depending on the project's requirements. For instance, a typical crawler crane might have a lifting capacity of 400 metric tons, suitable for handling many bridge girder types. Japanese heavy cranes are equipped with advanced technology to ensure safe and precise operations. They often come with features like telescopic booms, lattice booms, and jib extensions, allowing them to reach challenging locations and accommodate varying girder sizes. The cranes are operated by highly trained professionals who use remote control systems or modern cabin setups for maximum efficiency. One of the remarkable techniques employed in Japan for bridge girder installation is synchronized lifting. This involves the simultaneous use of multiple heavy cranes to lift and position girders. The cranes are precisely coordinated to ensure that the girders are placed accurately, minimizing the need for subsequent adjustments. Synchronized lifting is a testament to Japan's engineering prowess. In Japan, innovation is a constant pursuit, and this extends to bridge construction. Specialized lifting equipment, such as strand jacks and hydraulic gantry systems, are used alongside heavy cranes to ensure the smooth assembly of bridge girders. These solutions provide additional flexibility and accuracy in positioning girders. Safety is paramount in Japan's construction industry. Heavy crane operations for bridge girder construction adhere to strict safety standards and regulations. Measures are in place to prevent accidents and protect both the workforce and the infrastructure under construction. The Akashi Kaikyo Bridge, also known as the Pearl Bridge, is a prime example of Japan's expertise in bridge construction. This suspension bridge holds the record for having the longest central span of any bridge globally, measuring 1,991 meters. The bridge's massive girders, some weighing over 800 metric tons, were meticulously installed using heavy cranes and synchronized lifting techniques.